Hi guys, welcome to Easy Math.
Now the next theorem in the normal subgroup topic is, let n be a subgroup of G, then the following are equivalent. First one, n is a normal subgroup of G. Second, A inverse is equal to n for all A belongs to G. Third, A inverse subset of n for all A belongs to G, or A inverse contained in n. Okay. Fourth one, A inverse belongs to n for all n belongs to n and A belongs to G. In this theorem, they are asked to prove that the following four conditions are equivalent. How it is equivalent? Assume that first condition and prove the second condition. Next, you have to assume the second condition and you have to prove the third condition. And next, you have to assume the third condition and you have to prove the fourth condition. And finally, you have to take the assume the fourth condition and you have to prove the first condition. Then the four conditions are equivalent. Okay. Now we have to prove 1 implies 2. That means you have to assume the first condition and you have to prove the second condition. First condition is, let n be a normal subgroup of G. We know the definition of normal subgroup of G, that is an is equal to na. That means left coset is equal to the right coset for all A belongs to G. You have to prove the second condition, that is A inverse is equal to A. A inverse is equal to n. Therefore, you have to post multiply A inverse on both sides. How we multiply that A inverse? Since G is a group, n is a subgroup of G, every element A has an inverse, right? Therefore, A has an inverse, A inverse. You have to post multiply this A inverse on both sides. That means A inverse is equal to n A inverse. We know that A inverse is equal to E. So, if you have to multiply any number with the E, you get the same number, that is n. 1 implies 2 is proved. Now, we have to prove the second case, that is you have to assume the second condition and you have to prove the third condition. Second condition is, let us take A and A inverse is equal to n for all A belongs to G. Then obviously this condition A and A inverse contained in the normal subgroup n. There is nothing to prove here. It is an obvious condition. Therefore, second condition implies third condition. Now, we have to prove the third part, that is assume the third condition and you have to prove the fourth condition. What is third condition? Let A and A inverse contained in n for all A belongs to G. What you have to prove that A inverse belongs to n. That means this is a condition given A inverse contained in n. If you are choosing an element from this subgroup, that is n, then A inverse belongs to n for all n belongs to n. This is an obvious case. Hence, third condition implies fourth condition. Now we have to prove the last part, that is fourth condition implies first condition. What is fourth condition? Let A inverse belongs to n for all A belongs to n and A belongs to G is given, right? We have to prove that n is a normal subgroup of G. We have to prove that n is a normal subgroup of G. By definition, we know that it is enough to prove that the left coset is equal to the right coset. That is, you have to prove an is equal to na. For that, let us choose one element from this left coset. That is, let x belongs to an. Then clearly x is equal to a into some element from this subgroup, that is n for some n belongs to n. We know that A belongs to G, right? That means G is a group, therefore inverse element exists. Therefore, this an can be written as an into E. For that E, you have to write it as A inverse A. Again, G is a group, we know that. Therefore, this you can apply the associative property. Therefore, you have to put and bracket A inverse into A. In the given condition, that is the fourth condition, A inverse belongs to n. Therefore, this belongs to capital N. Since it is given that A inverse belongs to capital N. Therefore, AN left coset contained in the right coset. AN contained in NA, take it as equation number 1. Now we have to prove the second part, that is you have to take one element from the right coset and you have to say that that element is in the left coset, right? Now let x belongs to NA, then this can be written as NA for some n belongs to N. Obviously A belongs to G, we know that. Therefore the inverse element exists. Hence this ENA can be written as A into A inverse NA. Putting one bracket here, that is A into A inverse NA. We know that the fourth condition is A inverse belongs to N, right? A inverse belongs to N. But here we are having A inverse. I have to write A in the form of A inverse. Therefore, I am writing it as A inverse the whole inverse. Therefore, this term becomes A inverse N A inverse the whole inverse. Therefore, this is of the form A inverse belongs to N. The similar case, this element belongs to capital N. Therefore, X taken in the right coset is now in the left coset, hence NA contained in the AN. Name it as equation number 2. From equation 1 and 2, we are getting that left coset is equal to the right coset. By the definition, hence N is a normal subgroup of G. Hence N is a normal subgroup of G. Therefore, we are proving that fourth condition implies first condition. That means you have proved all the cases. 1 implies 2, 2 implies 3, 3 implies 4 and 4 implies 1. Hence the 4 conditions are equivalent. Hence the theorem. Now we are going to see the next lemma. N is a normal subgroup of G if and only if A inverse is equal to N for every A in G. That means if and only if means you have to assume the first condition and prove the second condition, and conversely you have to assume the second condition and prove the first condition. This is a very important lemma. Let us take N is a normal subgroup. You have to prove that A inverse is equal to N. By previous theorem, already we proved that N is a normal subgroup of G and second condition is A inverse is equal to N for all A belongs to G. That means 1 implies 2. We already proved that, right? By using that, we are getting A inverse is equal to N. Next, conversely, you have to assume that A inverse is equal to N and you have to prove that N is a normal subgroup of G. That means you have to prove the left coset is equal to the right coset, right? Here we have A inverse is equal to N. Post multiplying A on both sides. We are going to post multiply A on both sides. Therefore, A inverse into A is equal to NA. You have to interchange this bracket. Therefore, AN into A inverse A is equal to NA. Since A belongs to G is a group, the inverse element exists. Therefore, A inverse into A is equal to E. Since E is the identity element, we are getting AN is equal to NA. This NA is equal to N and therefore AN is equal to NA. Hence, the left coset is equal to the right coset. Thus, N is a normal subgroup of G. Hence, the lemma.
Thank you for watching. Don't forget to like, share and subscribe. Bye guys.